Hi, I'm Paul and welcome to Polymath. Today, differentiation. 3 exam-style A-level differentiation questions. I'm trying to grow the channel and get lots of maths video for you guys, so if you do fancy leaving a like, it would be much appreciated. Feel free to subscribe, you'll be updated whenever a new video comes along. Let's get straight into it. This first one, y equals 5x squared plus 10x over x plus 1 all squared. Show that, that's the derivative with some sort of a and some sort of n. Deduce the range of values for which the derivative is less than 0. Immediately, it's a fraction, and that says to me fraction action, quotient rule. Quotient rule is a formula. If you differentiate a fraction, which is u over v, you get du by dx times v minus u times dv by dx over v squared. Let's use it. dy by dx equals the derivative of the first thing on the top is 10x plus 10 times the bottom, which is x plus 1 squared, minus 5x squared plus 10x times the derivative of the bottom. The bottom differentiates to 2x plus 2 all over the bottom squared. X plus 1 squared squared, some have said, power 4. How are we going to get from this shambles to that beautiful A thing they've got there? Could expand it out. I choose not to because it looks painful, and there might be something else we can do here. If I pull out 10, then I'll get x plus 1, another x plus 1. So you'd actually get x plus 1 cubed. And then here you could actually pull out a 2 and you get 5x squared plus 10x times x plus 1. Now how did that help? Because, well, I can pull out an x plus 1 at least now on top. 10x plus 1 squared minus, let's multiply that out, 10x squared minus 20x. I'm not saying it's life-changing. I'm not saying, you know, the world is now going to pay me thousands of pounds in lottery winnings, but at least it's a little bit easier to expand the top now. That will go to 10 times x squared plus 2x plus 1 minus 10x squared minus 20x, x plus 1. The 10x squareds will cancel, the 20x's will cancel, and you're just going to be left with 10. Fascinating stuff, really, isn't it? And actually, an x plus 1 will also cancel. So, goodness gracious me, have you ever seen anything like that in your life before? 10 over x plus 1 cubed. How's that looking? The form is good. A, n, and x plus 1. A is 10, n is 3. Let's do part B. So we have our derivative from part A. Let's deduce the range of values for which the derivative is less than 0. Well, trying to solve for this, only one mark. More a thought process rather than detailed computation. It's a positive number on top, and it's a cube number on bottom. Now, when's a cube number going to be less than 0? Cube number will be less than 0 if it started less than 0, like minus 2 cubed is minus 8, for example. So it needs to be negative to start with. which means that x plus 1 should be less than 0. That means x is less than minus 1. That's your answer, really. Anything x is less than 1 will have a negative number on the denominator, which will give a negative number overall, negative meaning less than 0. Next question then. There's some sort of curve, x equals this time. Now that's a bit of a trigger warning, I'll tell you why in a second. Sine 2y, 4 sine 2y, get the derivative, use the small angle approximation, explain something, and then show something more with the derivative. Okay, trigger warning because if it's not y equals, the topic is implicit differentiation. We'll show you how to do that in a second. Small angle approximation doesn't often come up in a differentiation question, but here we are. Part A, x equals 4 sine 2y. Now with implicit differentiation, when you differentiate the x's, it does like normal, so x goes to 1. And when you differentiate the y's, it almost goes like normal. By the way, differentiating sine goes to cos, and you have to multiply that 4 by the 2 that's inside. It's a little version of chain rule, that. 4 sine 2y goes to 8 cos 2y, but for implicit differentiation, you also multiply by dy by dx every time you differentiate a y. That's how it goes. Rearranging, dy by dx equals 1 over 8 cos 2y. And what coordinates do we have to put in here? It's at the origin. 0, 0. There's no x's in there, it's just y equals 0. Get your calculator out or use that brain power to understand that cos of 0 is 1. So subbing that in, you'll get 1 over 8, which is going to be your answer for part A. Find the value of the derivative at the origin. Part B, use the small angle approximation to find an equation linking x and y. Okay, small angle approximation, sine x is approximately equal to x when x is small. I'll show you very quickly why. Here's a sine graph. And if you look near the origin, that's approximately a line of y equals x. So what they're saying is a graph, effectively y equals sine x and y equals x are both pretty bloomin' similar, close to the origin. So using that on the equation here, x equals 4 sine 2y is going to give us, in this case, x equals 4 times 2y, because it's sine 2y in this case. Let me just change our identity to mix to match that. You can use any letter there, it works for any letter. Here we're using the y, so sine 2y is approximately 2y close to the origin, and that means y equals 1/8 x. Interesting! Similar! Part 2, in fact, explain the relationship between the answers to A and B, I. Goodness me, well, there you go. The gradient of that line is 1/8, and the answer we got for the derivative of that graph was also 1/8. So the gradients of both these things at the origin are 1/8. Very nice. And part C, show that for all points lying on C, you get that. Well, yeah, admittedly, so far we only got the derivative at the origin being 1/8. Now they want it more generally. Well, we did have an expression for it, actually. We did have dy over dx equals something or other. It was, in fact, 1 over 8 cos 2y. Now we need to somehow transmorphificate that into what they have there. How are we going to do it? I'll tell you how we're going to do it. Using x equals 4 sine 2y in some sort of fancy way to transform the y's into x's. What we're going to do, oh, okay. I've got some ideas, I've got some hopes, I've got some dreams, square both sides. X squared equals 16 sine squared 2y. You won't square the 2, just be careful on that one. Why did I do that? Oh, now. X squared equals trig identity 101. Sine squared plus cos squared equals 1. So sine squared is 1 minus cos squared. Keep going a little bit. If we can make cos 2y the subject, we can sub it into the derivative. 16 cos squared 2y equals 16 minus x squared. Cos squared 2y equals 16 minus x squared over 16. When we take the square root, cos 2y equals the square root of all that monstrous stuff. So deleting that, moving the cos 2y up there, and now subbing it in to our dy by dx. Let's see what it looks like. 1 over 8 times that stuff. 16 minus x squared over 16. Probably not a bad time to check what the answer looks like. 1 over blah, 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 a root, ooh, lots of stuff in there, okay. Well, we're pretty close. We've got an x squared there. We've got a mildly irritating 16. Let's see what we can do with it. We probably want to get that 16th out, and we can do it because you do square root of top and bottom, it'll look like this. Root of the top and root of the bottom, well, root of 16 is 4. And then we can mix it with that 8. 8 over 4 goes to 2 root 16 minus x squared. I would call that quite the answer. So we've shown that for all the points the derivative is 1 over a times root of b minus x squared. Final question. And finally we're getting a graph, a picture of a graph after all this time, something to actually wrap our eyes around. The equation looks painful though, at first glance anyway. Let's see what we can do with it. Show that the derivative is that, then find the stationary points and play around with some function related stuff to find the range. Come on then. Derivative. Last time it was fraction action, so it was a quotient rule. This time it's two things multiplied, so it's product rule. For product rule, if you're differentiating two things multiplied, it goes to the derivative of the first one times the second one, plus the first one times the derivative of the second one. The quotient rule you usually get in the formula sheet, the product rule you don't get in the formula sheet. I'm going to write them out explicitly this time just because it looks a little complicated. U equals 4x squared minus 2, whereas v equals e to the minus. Now I can't even see that. Let me get my deep eye glasses out. It's minus 2x. We'll differentiate both of them. Du by dx goes to basically just 8x, because if you multiply that out, 4x squared minus 8, the 8 will disappear. That's all you're left with is the 8x when you differentiate the 4x squared. And this one, you are an exponential differentiation genius, and you know you just multiply the minus 2 down the front. Wonderful, wonderful to see. Plugging them into the formula, the derivative then equals 8x times e to the minus 2x plus 4 times x squared minus 2 times minus 2 e to the minus 2x. Beautiful. Tidy it up slightly. 8 to the x e to the minus 2x minus 8 x squared minus 2 e to the minus 2x. Now, you could expand this out now again. Like with that quotient rule one, You could expand it out. I wouldn't come for you. However, if you can factorise, I recommend it. Here, e to the minus 2x. If we do it, we're left with 8x minus 8 times x squared minus 2. Following which, 8x minus 8x squared plus 16. And I could have pulled out the 8 earlier, to be honest, actually, but let's do it now. 8e to the minus 2x. Pretty good time to rearrange it into the form that they want. Yep, that's 16 will go to 2, that will go to 1, that will go to 1, 2 plus x minus x squared. What a time to be alive. Part B now. Hence, find in its simplest form the exact coordinates of the stationary point. Note, they gave you the answer in part A. You could do part B even if you couldn't get part A. Please do that. Please don't capitulate and lose the rest of the marks if you can't do part A. I'm asking nicely for now. So they've given us it. 2 plus da 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 da. They like to write that e to the minus 2x at the end for reasons best known to themselves. Now, equals 0 for turning points, or as some might call it in this question, stationary points. And let's just make that crystal clear in case anyone's in any doubt, because I do still come across some of you who, you know, may not actually know that 100%, and it does upset me. It does upset me. But it's all right. I just cry for sort of 5 to 10 minutes, and then I get on with the next maths question. But the derivative is 0 for stationary points. So setting that equals 0. Now, here's a thing. Three things multiplied equals 0. So that means each of them separately could be 0. Wow, you could have 8 equals 0. Doesn't seem like the best maths I've ever experienced in my life, so let's discard that one. You could have e to the minus 2x equals 0. However, try it. I dare you. I dare you to do ln 0 in your calculator. Go on then. You're not going to do it, are you? You're not brave enough, because it's going to give you a math error. Also, if you think about an exponential graph, it doesn't touch the x-axis, so it never, certainly, never gets to 0, which would be y equals 0, which should be the x-axis. So no solutions to that either. We're just left with this middle quadratic chap slash chapette. Set that equals 0 and off we go. Do you know what? I'm not a big fan of that minus x squared. I really do quite like my stuff to be, my x squareds to be positive. So I'll move it across. Does it factorize? Does it factorize? Oh my goodness, it does! It actually does. It actually does. It's a good day. It's a good day when that happens. It works, doesn't it? Because you have minus 2x and then plus, oh, it's good stuff. So x equals 2, x equals minus 1. How on earth does that relate to the question? I kind of forgot now. Oh yeah, exact coordinates of the stationary points. Oh, looks quite nice in that picture. So we can see the minimum will be at minus 1 and that maximum will be at 2. Could do with the y coordinates. Let's do it then. Subbing back in to the original equation, you'll get for minus 1, the y will be, I'm actually going to do this in my head. I'm an absolute maverick, to be honest with you. For minus 1, you would get minus 1 squared is 1. Minus 2 is minus 1. Multiply it by the 4, minus 4. And e squared, because you've got 2 times minus 1. Minus 4e squared. Wow. And for x equals 2, you put that in, x squared is 4, minus 2 is 2, and you get 8. 8e to the minus 4. 8e to the minus 4. So, got our answer to part B for the exact coordinates of the stationary points. Part C, find the range of G and find the range of H. Well, let's get the range of the original one first. If you look at the picture, I'll re-sketch it down here. This low point is y coordinate wise minus 4e squared. Remember, y coordinates all that matters for the range. So actually for that, the range is anything above minus 4e squared. So minus 4e squared, f of x is bigger than or equal to that. And that's good to know because g of x is a transformation to f of x. Dust off the cobwebs on your transformation of graph certificate, which is lying in a cupboard, and you'll realize it's a vertical stretch by 2. So the graph is going to be vertically stretched, all the y coordinates doubled, so it'll be minus 8e squared. G of x has to be bigger than that. And I could draw that on very quickly. It's going to look something like that, a vertically double stretched version. Back to the original graph and checking out h of x. It's had the g of x treatment, and it's also got a minus 3. Minus 3 is a transformation outside the brackets. You know it, I know it. Shift it down by 3. So it's your doubly transformed graph, moved down by 3. Minus 8e squared minus 3 is the new coordinate of the low point. So in terms of a range, h of x would have to be bigger than or equal to that. Thanks very much, guys. 3, A-level, differentiation, exam questions, bingo, bango, bongo. Thanks for watching. I'd appreciate a like if you enjoyed this. Subscribe if you can. I'm going to keep more content coming. Have a lovely day.